All right, this is our last section of involving Chapter 2, and also it culminates the first unit of our study, mainly vocabulary and a small uh, inference factor about making conclusions from the simple graphs and data that we collected. This one is called Scatter Plots and Correlation and Regression. Okay, so in this section, we're looking at some mathematics involving analysis of confidence that the data, when plotted, has a direction. That a line can be oops, can be drawn, or that comes with that regression correlation. All right. So we're talking about a line that the data is going in a direction, pointing in some fashion. First, discuss the correlation and the role of the graph called scatter plot, and provide an introduction to the use of linear correlation coefficient. That's what our objective is. Provide a very brief discussion of linear regression, which involves the equation and graph of a straight line that best fits the sample paired data. So here we have paired data, meaning we have an x and a y, as in algebra. But we call this x and y a little bit different in statistics. We're talking about the existence of observed data at a specific time or date or occurrence or weight or all kinds of conditions that mean something besides x and y. And we're saying a line. Well, a line goes like this from left to right, or goes down for a negative, or stays constant. In each of these cases, we're saying, well, what does the data do around it? Well, the data can be like this of the scatter plot. So scatter plot shows that we can draw a line in this scenario. And of course, sometimes you'll have an outlier or two. And then on a straight line, they are in a cluster around that line. Well, what a correlation coefficient measures is the distance of each data measurement in a percentile from the line that can be drawn. And that makes the mathematics a reference point of validity into assessing if there is a connection in the data as to an output. So we're going to talk about first scatter plots and correlation. A correlation exists between two variables when the values of one variable are sometimes associated with the values of the other variable. In other words, there's a connection. Not a causation, but a connection. Causation happens seldom in statistics. All we can do is state what the data says. Correlation is not a reason for causation, and that's another condition of statistics. So we have to be very careful about output or evaluating. A linear correlation exists between two variables when there is a correlation and the plotted points of paired data, like I drew up here. This is a linear correlation. A correlation just means an observation of data going or trending towards some part. Scatter plot or scatter diagram is a plot of the paired XY quantitative data with a horizontal axis and a vertical Y axis, and each one of them state a position. Okay, so let's look at some examples here. And we're going to be discussing first the scatter plots and what we think is happening with the data, a general understanding of that scatter plot principle. So here we have the heights of presidents and the opponent who is running against them, their height. And so we're saying, okay, in a particular time, the president's height versus the opponent's height. Now let's look at a few and see what we can glean from this. This 169 centimeters to 173, shorter. 171 to 176, shorter. 190, taller. Uh, 192, taller. So I should be using those symbols for comparing. I should use it. And this is taller, 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 taller by a little bit, the same, and taller, taller, the same, less, taller, less, taller, and taller. So we have a lot more taller presidents than we have their opponents in measurement, just by the sheer count of what we can see. So we want to choose the graph that displays this data. And we're saying this is our X and this is our Y as the ordered pair of information to see if there is a connection with this particular condition. All right, so we're saying, okay, 169, which is this, what, 2, 6, 7, 8. So we're at 60, 160 on each of the graphs, and it goes to 200. So, and we started with the 169. So this would make it, and there's 8, right? And so we have 40. So each 2 is 10, right? So 170, I think, 180, 190. Yes, each one is 2. So if we have the 169, it's almost at 170, and that looks pretty good because it's the 169 is a 173. That's too high because it starts at 60, and again, this about 170, 180, 190. Okay, so this one is not that measurement of 173, as we can see. So this one is not either. This guy could be, but it's not. It's this guy. This guy has it, and we can see that the greater, now the 2 or less, and then we have the greater, greater, greater. So we can see that this group is the greater or equal to, but are those less than? And that would be the graph of this material. I would look for something that's close to what we stated, 172, and see what was going on with the graph. All right. So, does there appear to be a correlation? Not really, right? No, because we got all of these outside of that grouping. And so, no, this one's, all of them are yes except this one. No, does not appear to be a correlation because there is no general pattern to the data. All right. So here we have another one. And I would enlarge the graph when you're doing the homework, and that would help you. This says the table lists weights in pounds and highway mileage amounts, MPGs, for 7 automobiles. Using the sample data, construct a scatter plot. Using the first variable for the x-axis, based on the scatter plot, what do you conclude about a linear equation? Okay, well, this is easy because we got 1, 2, 3, 4, 5, 6, 7. So we can order them. 2405 is 38, right? So that's that one. I think that's the lowest. Then we have a 2985 gets 32 miles per gallon. And then we have a 3435, we get 30 miles per gallon. We can see a pattern, can't we? Then we have the 3525, and we get 28 miles per gallon. And then, so that's this one, this one, this one. Now I got the 38, 35, and we get 26 miles per gallon. And then we're in the 40s of weight. 4,050 pounds, and we get 24. The vehicle weighs that much. And then we have the last one, 4520, and we get 22. Well, we can see that the weight does have something that affects the mileage, MPGs. So we're looking at 24. So we've got a gauge here of 2,000 to 5,000 pounds. And we have 1, 2, 3, 4, 5. 5 in between, right? So that's 3. So we're saying, oh, this one is a little bit rough on that. So if this is 3, this is 4, and that's 5. Okay, so this is a 3,000, and this is a 4,000. That's what they're made up to be. So we started with a 2405. So this is a 25, this is 2405, and we get 38. That looks pretty good. This one does not. This one is about right here, and no, this looks like it is 10, 20, 30, 40. So this is 10. This is in the teens. No, that's not it. And this one could be it. So we got those two in the bottom that look that they might be the parts that we have. The next one is 2985. So here's our 3,000. 2985 gets 32. Okay, so this is this is 20, 30, and this is a 32. That looks pretty good. Okay, so this is that same position, but it's giving me exactly 30. So this one is wrong. So this is our solution. We'll double check the last one's 30, exactly 30 for a 34, 35, okay? 34, 35, there it is. So yes, this is the one. And then at the last one, 45, 20, it is at 22, 20 and a bit. That's correct. So this is a correct graph. So what do we notice? We notice there is a downward trend of miles per gallon as the weights increase. So we have a linear equation that could fit. We could draw a line. And is there a linear equation? The answer is yes. Now we have two yeses. As the weight increases, the highway mileage decreases. Yes, as the weight increases, the highway's mileage uh, in, increases. No, that's not right. So it's A. There we go. Excellent. Linear correlation coefficient R. Now this is an algebraic reference for the strength of the possibility of a line percent. So if the regression, the higher the percent, the more likely that a line of regression can be utilized, and shows a direct correlation between the paired data. And this is on paired data, so you got to keep that in mind. So this is what I got typed up for you. The linear correlation coefficient is denoted by a lowercase r, and it measures the strength of the linear association between two variables. Computed value of the linear correlation coefficient R is always between -1 and 1. That's very, very important. We can have it below the line or above the line. In either case, if it's strong enough, it should be good. If R is close to -1 or close to 1, there appears to be a correlation. And remember what a correlation is, a relationship of the paired. Okay, if R is close to 0, there does not appear to be a linear correlation. So here we're saying the larger the percent, the stronger the connection, right? The larger the percent, to 1 or -1, the stronger relationship of the paired data. This is a part that I found very interesting in the study of this material. Because I like to teach algebra, and correlation coefficient gives us a strength. And it says the number of pairs of data and the critical value of R. And that is the litmus test. And we're now associating assigned percentages plus or minus, it doesn't matter, um, for this correlation to give you the critical value of R, what it should be to be sound, to be relevant. The smaller the data, the higher the percent, closer to 1 it is. The larger, it tends to go to the 50 percentile. It doesn't go below 50 percentile, even though it would be high. Then we have this picture that I got from and I'm going to enlarge it. It says the correlation area, that means the value of the relationship of R, and then the non-correlation, which is a center part of that percentile. So if R is 591 thousandths, which is this value here, where it says no correlation, anything in this zone makes it linear. So that lets you know what the litmus test is. Well, this part right here, which is the difference between that 100%, because all of it is 1, right? From -1 to 1 is 100% of the data. And so if it's in the edges, then we're talking about the p-value that exists. So now we get to this p-value, which is a percentile. And it's, of course, in a decimal form. Only a small p-value, such as 5%, suggests, suggests that the sample results are not likely to occur by chance. That means it is strong. That the percentile of 5% or lower means that there's no way that some anomaly in the sampling can cause it to occur again. And so it says, and when there is no linear correlation, so a small p-value supports a conclusion that there is a linear correlation of two values. Small p-value. So that's all you need to know. The small p-value, 5% or less, is an also indicator besides the R, the correlation coefficient. So there's two ways of measuring if it's a linear relationship. So let's look at this data right here. For a data set of brain volumes, centimeters cubed, and IQ scores of 5 males. So we have 5 ordered pairs of volume IQ. All right, so we got 5 of these ordered pairs of males. The linear correlation coefficient, the R, is 493. Use the table available to find the critical values of R, and based on the comparison of the linear correlation coefficient R, the critical values, and what you conclude. All right. So let's talk about this. So we have our 1 and our -1, all right? And we know this is 5, so I'm looking at my chart at 5. And we have 878 thousandths. So in this case, we're saying plus or minus. Okay, so if I'm looking at this end, the -878, because it's less than that value, and over here it's the positive decimal 878, then anything that lies here has no correlation. It would have to be in this area here, So let's see what we have. Remember, our R lies, if this is 0, then it lies about right here. So there is no correlation. Okay. So remember, no correlation if we have, there's correlation if the R lives in the areas, either in the negative or the positive, of that critical linear situation. So we understand that our number, we already drew it up there, since the correlation coefficient, boy, if I could talk, right, is negative decimal 878 and positive 878, there is not sufficient evidence to support the claim of a linear correlation, because R equals decimal 4, I think it was 4, what was it, 493. It lies within this area here. All right, let's do another one, nothing difficult. Again, draw your little number line, you'll be okay. Remember, -1, 0, and 1. Here we go. For the data set of chest sizes, distance around the chest in inches, and weights, so we have chest size and weights as our comparison, our paired data. 11 anesthetized bears, so we have a total of 11 bears that are measured. The linear correlation coefficient for the data was R equals 931. Use the table available to find the critical values of R based on the comparison of the linear correlation. All right, so we're talking 11 bears. So we know that in our number line, we have a plus or minus decimal 602 as the critical values of R. So, okay, so at the negative, if this is the 5, well, the 6 is right here. So negative decimal 602 and positive decimal 602. All right, so this is the area of no correlation. Now, where is 931? Right, where is that? Well, if it's close to 1, so it should be right about here. Decimal 931 is R. Therefore, there is a linear correlation. Since the correlation of R is 931 thousandths, there is sufficient evidence to support the claim of a linear correlation, because lies in the area between decimal 602 and 1. So therefore, there is a linear correlation. So let's talk about some p-values now. Talk about some p-values. And I have two examples here. For the data set of brain volumes again and IQs, spelled Hannah, sorry about that. Five males um, were measured. The linear correlation coefficient is found, and the p-value 0.522. Write the statement that interprets the p-value. Now remember, on the p-value, uh, we have a very high p-value, right? So we're going to change it to a percent because they want it in percent. So we're talking 52 and 2%. 52 and 0.2%. The p-value indicates the probability of a linear coefficient that is at least as extreme as 52 and 2%, which is, and in this case, we're saying high. It is high because it's higher than our 5%. So there is not sufficient evidence to conclude that there is a linear correlation, brain volume and IQ in males. And that's because 52 and 2% p-value greater than the 5% p-value. Required, it's less than 5 or less than 5 required to say, yes, there is a correlation, because it's not in the endpoints of that restrictive evidence. Okay, here's the last one that we're going to do. For the data set of weights in pounds and highway fuel consumptions and PG, there are paired data. Fuel consumption amounts of 9 types of automobiles. The linear correlation coefficient is found, and the p-value is 0.009, 0.009, just 9 thousandths. Write a statement that interprets the p-value. The probability of a linear coefficient that is at least as extreme as, and remember we move it over to spots and then add the percent. 0.9%, which is very low, right? It is very low. So there is sufficient evidence to conclude that the linear correlation between the weight and the highway fuel consumption is in automobiles. So that means that decimal 9% is less than that 5%. So therefore there is a correlation. There you have it. We have completed chapter 2. Make sure you do all of the homework. You study everything that we've done. Make sure you have notes so when you take the test, you are proficient. Look at the review question listing so that you will be aware of what to anticipate. Thank you very much for listening.